Yesterday we had discussed the introduction about the segment routing. So I will just start from the same slides where we left yesterday. So we discussed like segment routing. Actually, it allows a node to send packets through the segment routing policy, and the policy will contain the ordered list of segments, and these segments are actually the instruction like how the packet should travel within the network based on the topology, and within the topology we can have nodes and we can have adjacencies which are our links, services or applications. So in segment routing there are two types of data planes. One is MPLS. So in case of MPLS, without doing any change on the we are going to use the same technology like the classical MPLS we have. We are going to use the labels, and then we can use the list of segments, and these segments could be IP addresses or could be list of labels as well. And then the when the device receives the list of segment, it actually process the packet based on the active segment or the top of the segment which we have. The second option for segment routing data plane is IPv6. So in that case we use the IPv6 routing header, and that is called the segment routing header, and in short we say SRH or SRv6. So for segment routing using v6, it is said that it is segment SR. Again here we have to give the list of segments that the packet should travel, and the active segment is processed, and when devices receive the packet, they actually keep on changing the destination address. So the next node, when it receives it knows where to send the packet. So there are few terminologies. One is like the segment. So a segment is just an instruction which a node needs to execute when it receives a packet, and then it will forward the packet based on this. And so the other terminology we have, that is the global segments. Global segments are the segments which are globally significant. That's mean within our segment routing domain, every router knows about them. Local segment, they are locally significant. That's mean only on the router which is which has that link connected. Actually, he only knows what to do with it. The next we have is the SID. We say segment identifier. So actually SID, it is used to identify the segment, and we have the example is like it could be an absolute MPLS label, or it could be an in case of IPv6 it could be the SRv6 SID, which would be an IP address. The next is the segment SR policy. So in that case the policy will have the list of SIDs or list of segments, and those needs to be executed in a certain manner which we when we build the policy, and then packet will traverse within the segment routing domain. So in MPLS, when we are using MPLS as a data plane, then the segment list is actually initiated or started by the ingress router, and same in case of IPv6, it is also initiated by the ingress router as well. The another terminology we have, that is the SR domain. So when we say the SR domain, actually it will represent the nodes or the router which are the part of the segment routing domain. SR global block. So this is the range that we provide on each router, which it's reserved for the segment routing label allocation. And when we specify, so this is our this range is globally significant. That's mean on the all the router they can understand about it. That's why we try to keep the same range. When we will have the lab, then we will see how we can configure this. Segment routing local block. So this is used for the assignments of the label for the links or adjacencies, and they are locally significant. Only the router which is assigning these labels, he actually knows what to do with this label. The other routers, although they will receive this information, but they cannot take the any action based on that. The next we have is the active segment. So the segment that is used by the router to process the packet. So in case of MPLS, this will be label, and in case of IPv6, it will be an IPv6 header, and inside obviously we will have the IPv6 address as well. The last we have, that is the segment list depth. So this is the number of segments in a segment list. So few of the devices, based on the vendor capability, actually they have different I can say different capability to support. Few of the devices, maybe they can support a longer list of segment, and we can have few devices which actually have limitation on the number of segments they can process at a time. The example could be like one device can maybe process 20 a list which has like 20 segments. Another device maybe that can process only 10 segments at a time. SR policy, in short we will say segment routing policy. So it is an ordered list of segment which are actually built or instantiated when we receive the packet, when the packet reaches to the segment routing domain. And in MPLS data plane, as I said earlier, it will be the labels, and in case of IPv6, it will be the list of IPv6 addresses. So the active segment that must be used to receive the to process the packets, and in case of MPLS, it will be the top label, and in case of IPv6, it will be the segment routing header. Like within the IPv6, we will see later on. Let me see in the slides if I have some introduction about the IPv6. So this is the IPv6 header. So we have the like version, traffic class, flow label, and then other fields. So actually if we are using a segment routing IPv6, then the next header field, actually this will have the segment routing header value. So the IPv6 packet will know like the next upper layer header or the extension header, it is the segment routing header, and after the basic IPv6 header, the segment routing header, it will be attached to it, and then it will have the other field, like the upper layer could be TCP or UDP, and it will be attached to it. So in the next header field, we can have different values. Like if we are sending an ICMP packet, it will have a value of 1. If it's we are sending an IPv4 packet using IPv6, it will have a value of 4. For TCP 6, UDP 17, and different value. Similarly, you can say IPv6 routing header, it will have a value of 43, and then within this IPv6 routing header, the subheader is the segment routing header, and this is the header format for the IPv6 routing header, and it will contain the list of the IPv6 which it will have. So we can see the segment routing header has the value of 4. So within the segment routing header, we have like two types. So one of them is the segment routing header. So as we said, in case of segment routing policy, the list of segment, it will be imposed or it will be added by the segment routing node at the edge, which is the first node when the packet are received, or it is the node from where our segment routing domain is going to be started. And how we can add this list? So this could be added by the network engineer, or like we are saying locally by an operator. That means who can configure a router. This is the network engineer or the person who is going to access the router and add it. The other way we can provision it is using the like netconf, or we can use the PCE. And when we are saying netconf, that means we are going to use maybe the controller, or maybe some other tools through which we are going to push the policies. When we are saying the PCEP, that means we are going to use the controller and then we are going to compute the path, and then controller is actually going to share this information with the segment routing domain, node. As we have seen, like in case of MPLS, we have different kind of operation like push, swap and pop. So similar operation we do in case of segment routing MPLS as well, and segment routing IPv6 in both cases, but just the names, they are a little bit different. For the push operation, when the packets come in and you need to attach the list of labels, or you need to attach the list of IPv6 addresses in form of a segment routing header, then this is called the push operation. This is same like we have discussed in case of LDP. Then the other one is the next operation. This is like we equivalent to pop operation in MPLS. So there we say we are going to pop the label. Here we say we are going to activate the next segment. So what does it mean? Like the still the packet has not reached to the ultimate node, and the node in the middle, they just need to process it and send to the next node. Continue operation is this is equal to the swap. Like the packet is in the middle and you need to swap the label. This is what we do in case of MPLS. But in case of segment routing, this will be like you need to it has not reached to the destination and you need to process it and activate the next segment. So these are like just a little bit names are different. Rest they are almost doing the same kind of thing which they were doing in case of MPLS. So if we discuss about the control plane, in terms of control plane, we have the option to have a centralized control plane, or it could be distributed as well. In case of distribution, the segments, they are going to be allocated by the IGP protocol, ISIS or OSPF, or BGP could also be used in some cases. Centralized, when we say that means we are going to use the controller, and from there we are going to specify, or we are going to distribute the labels in the control information in that case. The hybrid could be the combination of both of these, like the centralized and the distributed approach. So as we said earlier, we have the adjacency segments. So who is going to distribute them? So it's our actually IGP protocol which advertise the IGP segments, and then we have different extension in IGP like OSPF or ISIS. In order to support the segment routing, they have been extended, and there are multiple sub TLVs which actually they use to advertise the IGP segments. So these segments, they identify the information about the IGP. It could be related to the prefixes or the topology as well. And within the this we have the IGP segment which is like the global, and it is equal to we can say the nodes segments or the prefix segment as well. Within the node segment we have two types. Prefix SIDs we have two types. One is the node segments, another is the anycast segments. So in case of anycast, actually there could be a scenario where multiple nodes, they have the same SID, and they are going to use the one SID to advertise to other nodes. So if other nodes need to reach them, they can use the same SID. But in case of node SID, only one node is going to use the one segment, and other nodes, they are not going to use the same segment. The second type, it was the IGP adjacency segments. So this is the locally significant, and these are related to your links or the adjacency you have. So the node SIDs, they are used to identify the nodes as a destination. Like if you need to send a packet to a node, then you can use the node SID, and the devices in the middle, they can process, and the traffic will reach to the node ultimately. So the nodes in segment routing domain, when they when we use the IGP protocol, so the IGP protocol help us to distribute the information about the node seeds within the segment routing domain, and other nodes, they can use this node seeds to reach to this node. They can use the shortest path, and it could be ECMP aware as well. That means if there are multiple paths, then the equal cost path load balancing can happen as well. The another thing we can use, another concept is there, I will not go into detail at this moment, is the flexible algorithm within the segment routing domain, where you can specify some sort of constraint, and using those constraints you can calculate the path. So the node seeds, they are advertised by the IGP protocol, like we have OSPF and ISIs. These are the two link state protocol, and these are used to advertise it. And you need to manually configure the node seed on the device if you want to have this, and this could be like your NMS or the operator as well. So another type of node seed is ANICA seed, which if you want to specify if you want to use the same node seed for multiple nodes. So the nodes can have like their own node seeds, and on top of that they can have an ANICA seed. The example could be like everyone in this class or in this room, we have our own unique name, but as since we are in this room, so we can say like we are part of the SDN workshop. So someone outside, if we go outside, they can address us using all the people who belong to the SDN workshop, they can come on this side. So once this message could be received by all of you, and whoever will be close, he can actually take the action. So this actually applies to scenarios where you need redundancy, and like two nodes, they are actually serving the same service, and you want to send the packet towards them. What is the service behind? So you are actually using the ANICA seed. In that case, the node which is nearest one, it actually receives the packet and then forward it. Again, it is also advertised by the OSPF and ISIs, which are the IGP protocol is used in the segment routing domain. The third type, which like we briefly discussed, this is the adjacency segments, and they are related to the links that we have between different nodes, and they are only significant or only could be understood by the node where those adjacency are. The other nodes will have this information through the IGP protocol, but they actually cannot take an action. This is the real-time example could be if we reach to any roundabout and there is a tag, if you want to turn to this, go to this road, then take left. So only this action could be taken once you reach to that roundabout. If before that you have even that information, you cannot do anything unless you reach to that point. That's why we say it is locally significant, mean the other nodes cannot take any action. Others thing like this will be part of your so once if you put any instruction related to adjacency segment, once the packet reach to the certain node, then it will take action, and this action could be regardless of the IGP metric. Like even we saw in yesterday case, there was the metric was 100, but still we were able to send the packet regardless of the metric 100 across the link. Another type of SID or the segment identifier is the binding SID. Actually, this is used with the segment routing policy. When we create a segment routing policy, then that policy is actually assigned a SID, which is the binding SID, and it could be locally or globally significant depending on the scenario. And this actually allows us to initiate the policy, and the node on which it is actually configured that can impose this policy. So once the traffic reach to a certain node, if binding SID has been specified, then it actually removes the binding SID and attach the corresponding policy which is we have configured against the binding SID. And this actually help us to, as we discussed earlier, there is the concept of list of depth of segment list. So if some device they cannot support a very long list, then actually the other ways you maybe create the binding SID, it reach to the certain node, and there you again expand the list. We have BGP segments because since in the network we whatever we discussed that was the internal links and the nodes, and but we have the links going to the other networks and where you configure the BGP. So in order to do the traffic engineering using the segment routing domain on those links, we use the BGP segments. Within BGP segment we have BGP peering segments and BGP prefix segments. So prefix segments actually they represent a certain prefix within the BGP protocol, and the peering segment they actually represent the links or your peerings which are going towards the other nodes. Within the peering segments we have three types, which is like the peer node segment, and it will actually represent a BGP peer node, and peer adjacency segment this will represent the you have the peering through which link established, it will be come under the peering adjacency. And peer set is like if you have multiple BGP peers, then you want to use the same for multiple you will actually use the peer set to in order to if you want to send the traffic towards them. So this is like the grouping of the multiple BGP peers that will come under the peer set. So the BGP prefix SID, it actually it is a new optional transitive BGP attribute. Those who are aware with the BGP, actually in case of BGP we have the concept of transitive and non-transitive. In case of transitive, that means this could be passed on by the other nodes when they receive this information. So this is a kind of a BGP transitive attribute, and it is defined for the SR-MPLS, but now it is also supported by the SRv6 as well. So a BGP prefix segment, it is equal to a BGP prefix, and this prefix will have the BGP prefix SID attribute as well attached. So you can have a BGP prefixes where you do not have a BGP prefix SID attribute attached. In that case it does not qualify as a BGP prefix segment. So the label associated with the it will be actually passed on when we will have the BGP update message, and there are few of the TLVs which actually help us to propagate this information using the label index TLV and the originator sRGB TLVs. So this is the what we have in the BGP prefix SID attribute. We have the TLVs, and within TLVs actually it let us know the label index value which is attached to the prefix, and it gives us the information about the BGP speaker and what is the incoming label. The second is like the sRGB TLV. In that case it actually provides us the information about the sRGB block being used. So when we use in the segment routing MPLS, so in case of segment routing MPLS, the segment they will be the list of labels, and they will be in an order manner, and the segment which will be at the top of the label that will be executed, and there will be no change in the standard operation, like if when whatever the traffic we are carrying in form of VPN or non-VPN traffic using the segment routing MPLS, there will be no change. Like we will see in the lab, if even we remove LDP, the segment routing will be able to provide us the same kind of transport without any change on any other level. So the segment routing global block we briefly discussed is the set of the local MPLS label reserved for the global segments. So as a network engineer, you have to simply configure this on all the nodes and you have to provide a range. So in the example, we have the range of 16,384 up to 32,762. But certain vendor, they are actually using different range, like in case of Cisco, they prefer to use from 16,000 to 23,099. The local block, this is the set of the labels which are reserved or assigned to the local segment, and in this case we have the example of like we can assign a range of 32,000 to 768 to 65,535. But you do not need to specify. If you don't specify, whatever the range you have reserved for the global block, after that the next range it will start using for the local block. So how the label advertisement with the segment routing block. So the we have the how we identify the segments. We for the nodes only we allocate the absolute, or we can assign the index value as well. Then it actually takes the segment routing global block, and based on the index it will calculate the value. So in this case we can see we have defined sRGB here. The range is 100 to 99 and the index value is 101, and this is the IP address of the node. So all of these devices, they are going to advertise their range to each other and their index value. So once they receive this information, then as you can see the base index is same, so they can just add the index number into it and they will be able to calculate what value I need to use for the other neighbors. So in this case you can see for the P3 node, it will have the incoming label of 103, and the P2 node, it will use 103 for incoming and outgoing to reach to P3 as well. If it will use the PHP, then it does not require any outgoing label because it is the node directly connected, so it can just pop the label and send the packet without the label. But for P1, for sure, it needs the incoming label and outgoing label to reach to P3. So it will use the index value like 103, and it knows what is the segment routing block, so it will add this into it. Similarly, for the P2, sorry, I have said it wrongly. Actually, in this case, we are saying the absolute value. That's why it is using 102 or 103. Otherwise, it will add the index value within it. Here we are saying, okay, this is the actually the SID it will have. So here the index could be 3, and it will add 100 into it. That's how it will become 103. And here the index is 2. It will add 2 to 100. It will become 102 for the P2. So what is the incoming label mapping for the P2? It will be 102 on all the nodes. Only the directly connected node, they will have two kind of mapping for it. One is without PHP, another is with PHP. For P1 similar, it will send 101, and the other nodes, they will have the 101 to reach to it. Can anyone tell me why P3 does not have no PHP option? Why always we see P2 has with PHP, without PHP? Yeah, because we are seeing in this case the label mapping for P1, and for P1 the P2 is directly connected. That's why it can send the packet with label or without label as well. So once it receives the packet from P3, it reaches to P2. So if the instruction from P1 is to send the packet with label, in that case it actually do not do the PHP function. It will add the null label, which is the 0, and it will send the packet. But with PHP it will actually send it actually removes pop the label and send label 3, which is the implicit null in that case. So by default it is the implicit null that it will pop the label, and instead of the actual label it will send the label number 3. But if you want to retain the MPLS label till the last host, then you have to specify or configure this information on P1, and then it will be able to share this information with other peers. Okay, when you are sending me packet, you need to retain the label. So it actually keeps the label informed, like it just sends 0 label. So in that case, the use case is using it for the quality of service. So when we have some traffic coming into our domain, MPLS domain, and we are doing some quality of service, and we want to retain that information end to end, then actually we use the no PHP function. So another concept is, like, even you can define different range on the routers, still it will work, but in that case your label mapping will be different, and you in the troubleshooting you can get confused as well. So it's better to use the same range for all the router, especially for the sRGB, because obviously the local range we are not going to define. So if you have a different range on different devices, so in that case they actually use the index value and add it. Like if we have a node 1 and the sRGB is from 33,000 to 767 up to 16,000, sorry, starting is from 16,000 and ending at the 32,000. So if we say absolute value, then we can add 100 to the base and it will give us 16,484. For node B, if we have like a different range, which is starting from the 65,000 and going up to 131,000, so it will, once it receives the information from node A, so it will use the like the index value of 100 and add it to the base, which is 65,536. So it will get a different number. So in that case, your incoming label mapping from node B towards node A, it will be 65,636. So the label advertisement for different sRGB, we can see how it is advertised. So for P3, we have the sRGB is 300 to 399, and for the other nodes we have 200 to 99 and 100 to 199. And we can say the index value is 3, 2 and 1. So it is going to advertise its index value to other two nodes. So once they receive this, so although it will calculate its own index as well for its own identification, so it will add the index 3 to the base, and it will get a 303 number. So this is its incoming label. But from the perspective of P2, since its sRGB starting from 200 and going up to 299, so it will use the index value 3 and it will add it into its own sRGB base. So although it will receive the 300 from P3, okay, the outgoing label is 300, but for its own identification and to advertise to other node, it will add the 3 to 200, so it will become 203, so it will add 203 to P1. So now the P1 will receive 203 and it will also receive the index value which is 3, so it will add 3 into sRGB base, so 100 and plus 103, it will become 103. So now you can see by changing the sRGB, we have a different incoming label mapping. And if I have a traffic coming from P1 side, coming from this side and going towards the right hand side, so it will add, like it will add the label to send towards P2, it will add the label 203. So it will add the label 203, P2 will receive the 203 and then it will swap the 203 with 303, because P3 can only understand 303, it cannot understand 203. So now by changing the label, even you are doing some sort of complication, and you have to swap the label just like the LDP. We have different label in case of LDP. Do you have any question? I'm just trying to go slow so you are able to digest it. Similar for P2, it will, since we have a different value, so it will be 202, 102. For P1, 101, it goes to P2, it will be 201, and once it reaches to P3, it will be 301. So let's now discuss what will happen when we will have the when we need to provide the VPN service, or we need to provide the transport for any of the host which is connected here. So although in this case we are going to discuss the VPN, that's why we will have the service label. So who is advertising this label 1024? Since when we configure this link between P2 to C2 under the VRF, then the P2 actually assigns a service label for this VRF, and it advertises this service label to other P2 where the same branch for the same customer has been configured. So P1 will receive the label 1024. That means if C1 need to reach to C2, it will send traffic to P1, and P1 will use the label 1024 to encapsulate this traffic with this VPN label and send towards P2. Similarly, the P1 will also advertise the label for the C1, whatever the label would be, it will be advertised to P2. So our objective in this case is to deliver the traffic between P1 and P2 using the shortest path, and we are going to use the segment routing in that case. And you can notice what is the detail we have in this case. We have specified also the SID for each of the nodes. That means we have, this is the actual SID that they are going to use. It has been calculated based on the index value. So you can imagine here the index value will be 122. That's why if you add into the base, it will become 222. Here the index value is 6. Index value is 5, 4, 1, 2. That's why it is 101, 102, 103. And we are using the same segment routing global block. So what will happen in this case? This is our shortest path based on the metric, because here we have specified metric 100. That's why it is from here the metric become 40. From here it becomes 10, 110, 120 and 140. So how the incoming label mapping will be? So if we take the example of the P3 in this case, so it will have incoming label of 22, which is advertised by the P2, and the it will have the outgoing label 222, which is advertised by P2, and incoming label it has calculated based on the index value. So index value advertised by P2 towards P3, it is 122. That's why it will add 122 into the base, which is 100. So it will get 222. Similar for all other nodes, it has calculated the incoming. Obviously, it has received the incoming label, and then outgoing it has calculated. So you can see we are not like listed all the incoming label mapping for all the node. Only we have listed for the P2. So for P2 on P6, P2 on P6 we have 222. Again on P2 we have 222. On P5 we have 222. For P1 we have 222 for incoming and outgoing. And same is for P1. So that means if P1 need to reach to P2, it will just add the label. It will use the label 222, and then all other nodes, they can understand this label and they can forward the packet. So that's why I was saying that the node sits, they are globally significant. So all the nodes, they can understand what needs to be do with the 222. So let's see how the traffic is forwarded. So traffic comes in, whatever the traffic payload is, it will once reach to the PE1 router. So it needs to push two labels. Why we need to push two labels? Yeah, one is the service label, another is the, we can say another name, transport label. So the first one is the VPN label, service label, and the second is the transport label, and in this case the transport label is the SID for the PE2 node. So we only need to add the service label and the transport label, which is 222. So once this this information with this like this is our order list of segments, which is only we have one segment in this case, and it will go to P1 router. So what does P1 do? Based on the incoming label mapping, if we see what is the incoming label mapping for the, so you can see it has 222 and 222. So if incoming label is 222, it just need to swap it with 222 and forward the packet. So the next node, it will again receive the payload with service label and transport label, and it will swap it based on its incoming label mapping, and it will forward. Then P3 will also forward. So why the P2 has not sent the packet towards P5? Because we are just saying go to P2. So we are here. Now P2 need to send the packet towards P2. So why it is sending on this link? Why not on this link? Yeah, because it needs to use the shortest path. So if you calculate the metric from P2 towards P2 using this path, so it is 10 here and 10 here. But if you use this link, it is 10, 100 and then again 10. Maybe you have noticed this statement at the bottom. All the IGP like the metric on all the links is equal to 10 unless otherwise identified. So we have only specified metric 100 here. That means all the other links, they have metric 10. So because it can use the shortest path, and using the shortest path it needs to forward the packet, although it can use the equal cost multipath as well using the while using the shortest path. If the both of the path they are having the same cost or the metric is same, then it will use the load balancing. So once it goes to P3, again P3 using the shortest path, it will send the packet towards P2, and based on its incoming label mapping, it will just swap and send towards the P2. This is without the PHP, because it has not popped the 222. It has sent the label, both the transport label and the service label. So now the traffic has reached to P2. What does P2 will do? Can anyone want to explain? So what is P2 doing in this case? Although it's written here, no, it need to go in a certain order. So first it will execute the top label. So first it will remove the 222 transport label. Then based on the service label, it needs to identify who is the end customer or who is the like the destination where it needs to send the packet. So based on the this service label, it can identify the VRF, and then it will remove this label, and after that it will just forward the payload to the CE2. So do you think it's doing the same what we were doing in case of LDP, or it's different? When we were doing the using the LDP to provide the layer 3 VPN service or the VPN service, were we doing the same things, or we are now doing something different? Swap the label.
Labels, yes.
Yeah. In that case, we also swap the labels, but we swap it with different. The incoming and outgoing label, they are different. In this case, we have the same label, and we are swapping the incoming and outgoing same label with the same label. The only difference is because our sRGB block, we are saying it is same and it's globally significant. That means we do not need to change on the other devices. If we keep it same, it will be easy for us to check in the trace route, and we will see, okay, the same number is changing and it is reaching to the destination. Because yesterday when we took the trace route, maybe you have noticed, we saw two labels. One was the VPN label when we did the trace route from within the VRF. So one label was changing on the left hand side. On the right hand side, there was a slash and then the label. It was remaining same. So our VPN label will always remain same regardless of the LDP or the segment routing. But only the service label, the transport label, in case of LDP, it changed. In case of segment routing, it will change if you will assign different sRGB on the nodes. If you will use the same sRGB, your transport label is not going to change. So let's see the second use case where we can have the ECMP as well. So in this case, our objective is to deliver traffic between P1 to P2 via the shortest path through the IGP. So how our incoming label mapping will be, because we are using a different sRGB in this case. So you can see the incoming and outgoing label map, they have changed. So every device will calculate the outgoing label based on the incoming label based on its range. Like on P2 we have the sRGB range 800 to 899 and the index value is the 222. So that's why it will add 222 into 800 and its own incoming label map, it will be on, like SID will be 822. It will advertise 822 to other nodes like to P6 and P3. It will advertise 822 and then P6 it will based on the index value is 222, it will add 222 to 700. So the incoming label, it will become 7222 and it will advertise 7222 to other nodes. I think maybe there is a mistake here. It should be 7222, not 3222. Yes, on other devices it's fine. It will have 300, receive 3222, then add 222 to 200. It will become 222, and here it will receive 222. It will add the 22 into 100, and it will become 122. So in this case, once how the traffic forwarding will happen. So once the traffic comes in, it will add the service label and then the transport label. So since it's the outgoing label on P1, it is 222, so it will add 222, not 122, because 122 it can use once it receives the traffic with 122 label. So since this is a VPN traffic, so C1 cannot use 122. If C1 trying to do that, that means he is attacking or he is doing something wrong with your segment routing domain, and you need to protect your segment routing domain. So any devices which are not part of the segment routing domain, they should not be able to send the packet with the label. So you need to protect it, or you need to block that. We'll see how we can do that. So it will again add 222, but in this case, since we have a different sRGB defined on the devices, that's why every device will, based on its incoming label map, it will swap the label. So it will swap 222 with 322, then the next will swap 322 with 422, and it will keep on happening till the traffic reaches to the P2. Again it will remove the labels and then send the packet without the payload. It should be remain same, because then it will become easy for you. Okay, this, when you will see the trace route, you will be able to see, okay, it is going to a certain node and all the devices whatever the path it is taking, you can see it will be easy. Otherwise, if it changes, then again you have to go there and see what is the range defined here, and you have to calculate, okay, what was the index, because when things goes wrong, then sometime you have to go into very deep, and you don't know like where you will end. So the next use case we have for the traffic engineering. So our objective in this case is to deliver the traffic from P1 to P2, and the traffic should pass from P2 but avoid the link from P2 to P3. So we want to avoid the link from P2 to P3, and but the traffic should go to P2 but not over this link. So in this case we need to give the list of segments to fulfill this requirement, because if we do not provide this list of segments, then the P1 node, it can once the traffic reach to P2, it will use this path based on the shortest path, because here you can notice the metric across all the links it's same, we have not specified 100 here. So how the incoming label mapping will be, since sRGB is same, so 222 will remain same, and so how the traffic forwarding will happen. So in this case the P2 need to push a list of labels to fulfill this requirement. So this is your VPN label, first one, bottom of the stack, 1, 2, 3, 4. After that, or your top label should be the first label that needs to be processed. So in this case we have specified 102. Why we have not specified 101? Why we have given 102 directly and not the device before that? Yes, because on P1 we are saying go to P2 first. So it actually first itself the P1 will process the top label. So in order to reach to P2, we can see the metric from here is 10 and 10, 20, and the second path is 10, 10, and again 10, it will become 30. So that's why the top path, it becomes our desired path. So from here to here it is 20. My writing is not so bad, but here it is like this. So from the bottom it will become 30. So that's why if we just put the top label 102, so it will reach to P2. So our objective was to reach to P2 and then go avoid the link, which is then avoid this link and use the alternative link. So in order to give this instruction, we are saying go to P2. Okay, so it will reach to P1. P1 will, what it will do, it will swap it. So it will swap 102 with 102. Then the traffic will reach to the next node, which is the P2, and after that what it will does, it will execute the second instruction, which is go to 105. So if you calculate from here 10, 10, it is 20, 30, 40, but from here this direct link is just one hop away, and here we have 10. That's why it will reach to the P5 using this link. So it will pop 102. Why it will pop? Because this instruction it has executed. No, we do not need this anymore. Another thing we said, it will always execute, or it will always take action on the top of the label. So if top label will remain 102 once the traffic reach to P5, so P5 cannot take an action because it is related to this node. Another question, why the P1 has not popped the top label? Why the P2 is going to pop this? Because the node, once it receives a packet, if the top label does not belong to it, it will swap it. But the node, which node, if it receives a packet and the top label is same as its own node label, or the node which it can identify itself, then it needs to pop it, and it needs to see what is inside. So once it will pop 102, then it will be able to see 105 and take action for the 105. So first it pops, then it will swap the 105. It will pop and then send the towards the 105, because on the next level it needs to take the action. So this is swap, and this is kind of pop, and then the continue operation is happening. Once it reaches to P5, again the top label is same as the node, so it will again pop it and forward the packet to the next node. So here the next instruction says go to 222. 222 is your P2. So it will send the packet based on the shortest path. So since path from here is 10 and 10 20, and the upper path it become 30, that's why the packet will go from here. Once it reaches to P6, it will again, since the top label is not same as the local, so it will just swap and send towards the 222. And once it reaches to 222, again it needs the top label is same as the local, it's equal to the node seed we have here, so it will pop it, then it will be able to see the service label, which is 124. And since 124 it notes, it belongs to the VRF which has been configured here, and the C is attached, so it will then pop it and send the traffic towards the C2. Any question you have? Okay, so we can discuss the next use case. So now we have again specified the metric 100 at the bottom. You can see we have specified the metric 100 here, but our objective is same. We want to reach to P2. First we want to go to P2, but we want to avoid this link, which is the link between P2 and P3. We do not want to use this. So how in this case, or what will be our list of segments, the ordered list of segment, what it should be? One hint is, like here you have a metric 100, now you need something different than the previous example to move the traffic from P5 to P6. So can you think of the list of segments? So here we were having 102, 105, 222. So this was the our node seeds. So what different we have to do if we have a metric 100 here? If metric 100 is here, so what different we have to do? Sorry? P4 to P5, but how we will send traffic from P5 to P6 since metric 100 is here? Okay, so if I add 106 here after 105, okay, let me add. So that means I will add here another label which is 106. So let's process it. So P1 will send this list, it will send to P1, P1 will take the top label which is 102, so it will swap, send the traffic towards P2, it will see the top label is same as its local label, so it will just remove it, it will remove this 102, and now our after the traffic P2 is forwarding, we have 106 here. So we also have 106 after P6. And once the traffic reaches to P5, so we will have 222, 106 and 222. So it will have 106 and 222, because P5 will just pop 105. Okay, now P5 will execute the instruction for the 106, and it needs to use the shortest path. So the metric is 100 here. It will calculate the metric from alternative links. Okay, 10, 20, 30, 40, 50, 60 and 70. So 100 is here. From if we goes from this direction, it is 70, and if we goes from this direction back, so it will be 10, 20, 30, 40. So instead of sending packet here, it will send the packet back to P2. So now once the packet reaches to P2 will see top level is 106. So it will swap 106 with 106, and based on its shortest path 10, 20, 30, it will send the packet towards the P3, and P3 again it will swap, it will send to P2 will send towards P6, and P6 will just pop it. It will see, okay, next is 222, it will send the traffic back. But our objective was to send traffic from P5 to P6. So using this list we cannot achieve that. So what different we have to do, or what is the another option? But we in segment routing we do not want to use the policy based routing. So remember, we have discussed the adjacency segments. So far we have just used the node segments. So in this case we have to use the adjacency segment, which was similar to like reaching to a roundabout and then taking left or right. So it's similar, like we are saying to driver, okay, reach to this roundabout, then from there once you reach, take right, and then you will reach to the destination. So we have to specify the instruction to use the link from P5 to P6. Although the metric is 100, if we give this instruction, then it will go. So what will be our label? I will just skip it. Only you need to note here we have 106, but this is your local label. This is your adjacency segment 1001 to P6. That means if P5 want to reach to P6 using this link, it can use the label 1001, because 106 is the node seed and 1001 is the adjacency seed. So it will first, this is the same example like we discussed earlier. Without the adjacency segment, traffic will go, it will reach to the P2 will pop, it will send to P5 will send it back, because based on the shortest path is from the above link, it will send it back, it will reach to P3, then again to P2, and it will be sent to the CE. In this case, because we have not specified 106, the traffic will not go to P6, because the tops is 222. So once it reaches to P2, it will, since the top label is same as P2, it will pop it and see what is the service inside. But if we specify 106 before the 222, in that case P2 has to send towards P6. So our objective has not been fulfilled. Like we want to use this link, go to P2 and then use this link. So this is not what we wanted to achieve. So in order to achieve this, we have to use the adjacency segment, and we have to include the adjacency segment for this link, which is 1001. So in this case, this will be our desired list. We have 102, 105, 1001, 222 and 124. So P1 will send towards P1, since top label is different than the local seed, it will then send towards, swap it and forward towards P2. P2 needs to pop 102 and send towards the P5. Once it reaches to P5, so since the top label is same as the local seed, it will pop it and see what is inside. So it will be able to see the next label that it needs to process is 1001. Okay, so based on this 1001, it knows that 1001 means send traffic over this link. So it will send the traffic over this link, and once it reaches to P6, so the top label is 222, that means it needs to send traffic towards P2. So the traffic will reach to P2, then it will, based on the top label is same, so it will pop it and then pop the VPN label as well and send the payload. It can change. If you will, maybe your link labs, it can change. I have to see in the lab. But it's not fixed. Since it's dynamically allocated, so it can change. Maybe you have 1001 here between P5 to P6, and between P2 and P5 you have also 1000, because this is locally significant. That means each node can use the same number even to identify its own links. But this 1001, even the other routers knows about it. If we have like different list of segments, let me erase it and see, if we do not put 105 here, okay, and traffic reaches to P2, okay, and P2 pops the 102 and the next is 1001. So in that case P2 cannot do anything because it doesn't know what is 1001, where it needs to send the traffic using 1001. Although in the IGP it will have this, it will receive from P2 like this information, but it cannot take any action since the link is not attached to it. Okay, we can go for the break. So we can have a 22 minutes break, sacrifice 8 minutes. In fact, it's now 10, so we will start at 11.